On the 6th of December 1941, the Japanese Imperial Navy sailed towards Pearl Harbor. 2 days later, America declared war on Japan. Within the week, Germany and Italy declared war on America. President Franklin Roosevelt addressed a joint session of Congress with sobering arithmetic. America possessed 2,900 combat aircraft. Germany fielded 15,000. Japan operated 4,800. America's Navy counted 347 warships. Japan had 395. But the numerical disadvantage was only the beginning. The true crisis lay hidden in something far more mundane: tires, hoses, gaskets, seals, electrical insulation, and countless other components that made modern warfare possible. Every one of them required rubber. And 92% of the world's natural rubber came from Southeast Asia, now under Japanese control. America consumed 600,000 tons of rubber annually. The strategic materials stockpile held 540,000 tons, roughly 10 months' supply, if consumption could be frozen entirely. It couldn't. Military production would demand exponentially more. The Army required 100 pounds of rubber per soldier. A tank needed half a ton. A bomber demanded a full ton. A battleship required 75 tons. The Navy's construction program alone needed 84,000 tons annually. The Pentagon calculated requirements: 842,000 tons of rubber needed in 1942. Current domestic production capacity: 8,000 tons. The mathematics was brutal. America needed to increase rubber production by 10,000% within 12 months whilst simultaneously fighting a two-ocean war. The dependency was absolute. Goodyear, Firestone, Goodrich, and U.S. Rubber had spent decades perfecting natural rubber processing. Their engineers understood plantation rubber's molecular structure, its vulcanization characteristics, its behavior under stress. Synthetic rubber existed, but only in German laboratories. IG Farben had developed Buna S, a styrene butadiene compound, over 2 decades of research. German plants produced 15,000 tons monthly. But IG Farben was German. Enemy patents couldn't be licensed. Enemy expertise couldn't be borrowed. The rubber crisis threatened to strangle American military production before a single factory could gear up. Problem: every aircraft tire, every tank track, every military vehicle seal would fail without rubber. Solution: unknown. Timeline: 12 months. Probability of success: 0. William Francis Gibbs had designed the Liberty ships that would carry American forces across the Atlantic. But even Gibbs's genius couldn't solve the rubber shortage. The ships required 18 tons of rubber each just for hull gaskets and engine seals. Edward Stettinius, chairman of the War Resources Board, studied the projections and reached a grim conclusion. Without synthetic rubber, America couldn't sustain military operations past 1943. The stockpile would be exhausted. Civilian automobile use would cease entirely. The economy would collapse under transportation paralysis. Then someone remembered Waldo Semon. Semon had been born in 1898 in Demopolis, Alabama, the son of a cotton broker who moved the family to Seattle when Waldo was 3. Nothing in his childhood suggested future industrial revolution. He was competent at school, interested in chemistry, and completely unremarkable. In 1920, he graduated from the University of Washington with a chemistry degree. In 1923, he completed his doctorate at the University of Washington, studying phosphate chemistry. The job market for chemists was dismal. Academia offered poverty wages. Industrial chemistry meant repetitive quality control in somebody else's factory. The B.F. Goodrich Company in Akron, Ohio, hired him in 1926 for $2,400 annually to work on rubber adhesives. The assignment was mundane: make rubber stick to metal better. Semon worked in a laboratory measuring 12 feet by 15 feet, surrounded by beakers, Bunsen burners, and the perpetual stench of vulcanized rubber. His supervisor gave him 6 months to show results. If he couldn't improve adhesion, perhaps he could find something else useful. Goodrich had been experimenting with polyvinyl chloride since 1913. PVC was a polymer discovered accidentally by German chemist Fritz Klater, who found that vinyl chloride gas, when exposed to sunlight, formed a white powder. The powder was useless. It was rigid, brittle, and decomposed at processing temperatures. Every attempt to make it flexible failed. Every attempt to process it into useful shapes resulted in charred garbage. Goodrich owned American rights to Klater's patents, but couldn't commercialize the material. The company had invested $50,000 in PVC research with nothing to show for it except laboratory notebooks full of failed experiments. Semon approached the problem differently. Instead of trying to soften PVC through chemical modification, he tried dissolving it in solvents and adding plasticizers. On a Tuesday morning in 1926, he mixed PVC powder with a high boiling point solvent called tricresyl phosphate and heated the mixture to 160 degrees Celsius. The powder dissolved. He poured the liquid onto a sheet of metal and waited for the solvent to evaporate. It didn't evaporate. It stayed mixed with the polymer. The result was a flexible, waterproof, chemically resistant material that could be processed at reasonable temperatures. Semon had invented plasticized PVC. More importantly, he had invented a rubber substitute. Goodrich management wasn't interested. They were a rubber company. Their expertise was natural rubber. Their customers wanted natural rubber. Their factories processed natural rubber. Some experimental plastic that smelled terrible and required entirely new manufacturing processes had no commercial future. Semon was told to return to adhesive research. He ignored the directive. Working nights and weekends, he refined the plasticizer formulations. He discovered that different plasticizers produced different properties. Dioctyl phthalate made the material softer. Dibutyl sebacate improved low-temperature flexibility. Trioctyl tremelitate provided heat resistance. By 1928, Semon had 43 formulations producing PVC materials ranging from rigid pipe to flexible sheeting. Goodrich management remained unimpressed. The company filed patents to protect Semon's work, but devoted no resources to commercialization. The patents listed Semon as inventor, but Goodrich owned them entirely. Semon received his $2,400 annual salary and nothing more. The breakthrough came from an unexpected direction. In 1931, Union Carbide Corporation needed a corrosion-resistant coating for chemical storage tanks. Someone mentioned Goodrich's PVC patents. Union Carbide licensed the technology and began commercial production of PVC compounds. Suddenly, Goodrich management realized they owned something valuable. In 1933, Goodrich launched Corroseal, a PVC material marketed for chemical resistance and electrical insulation. Sales were modest, $47,000 in 1933, $180,000 in 1934. The automotive industry discovered PVC in 1935. Ford Motor Company tested Corroseal for electrical wire insulation and found it superior to rubber. It didn't degrade in oil. It resisted ozone. It maintained flexibility across wider temperature ranges. Ford placed an order for £12,000. General Motors followed with £34,000. By 1937, Goodrich was producing £2 million of Corroseal annually. Semon was promoted to section head and given a 15% salary increase. But legal complications emerged. Goodrich marketed multiple PVC formulations under different brand names: Corroseal for chemical resistance, Geon for electrical applications, Plyovic for films. The branding created confusion. Customers thought they were buying different materials. Competitors claimed trademark violations. In 1939, Goodrich consolidated everything under the Geon trademark and established a separate PVC division. Semon headed the technical department, but didn't control the business. His inventions had generated millions in revenue. He remained a salaried employee. Then came Pearl Harbor. In January 1942, the War Production Board issued Directive No. 4. All synthetic rubber research was to receive unlimited funding and maximum priority. The Pentagon needed rubber substitutes for 847 different military applications. Natural rubber worked for most of them, but substitutes were needed immediately. Someone at the War Production Board remembered that Goodrich was producing PVC. Someone else remembered that Waldo Semon had invented flexible PVC. On January 15, 1942, Semon received a telephone call from Washington. Could PVC replace rubber? How much could Goodrich produce? How quickly could production scale? Semon studied the requirements. Aircraft fuel tanks required flexible, fuel-resistant linings. PVC could do that. Electrical wiring needed insulation resistant to oil, heat, and vibration. PVC could do that. Raincoats, ponchos, and field shelters required waterproof fabric coating. PVC could do that. Tank periscope boots needed flexible, abrasion-resistant covers. PVC could do that. The material couldn't replace rubber entirely. It couldn't match rubber's elasticity for tires or engine mounts, but it could substitute for rubber in hundreds of applications, freeing natural rubber stocks for critical uses. Semon claimed Goodrich could deliver 500 tons of PVC monthly by June 1942 and 2,000 tons monthly by December. The War Production Board issued Contract W330345678 on 1 February 1942. Goodrich would receive $8.4 million to expand PVC production. The contract specified 24,000 tons of PVC compounds delivered by December 1942 at $350 per ton. Penalty clauses assessed $5,000 daily for delivery failures. The transformation was extraordinary. Goodrich's Akron plant had one PVC production line capable of 200 tons monthly. Semon needed 10 times that capacity in 10 months. Plasticizer supply was the immediate bottleneck. Tricresyl phosphate was manufactured by one company, Monsanto, which produced 40 tons monthly for the entire United States. Semon needed 400 tons monthly. He contacted Union Carbide, Dow Chemical, and DuPont. Could they manufacture plasticizers? Union Carbide built a plant in Texas. Dow expanded facilities in Michigan. DuPont constructed a factory in West Virginia. By May 1942, plasticizer production reached 380 tons monthly. Polymer production was the next challenge. PVC required vinyl chloride monomer, which required acetylene, which required calcium carbide, which required limestone and electricity. Goodrich operated no calcium carbide plants. They bought carbide from Union Carbide, which was operating at full capacity, supplying acetylene for metal fabrication. Semon convinced Union Carbide to build a dedicated calcium carbide plant at Marietta, Ohio. Construction began in March 1942. The plant entered operation in July 1942, producing 500 tons of calcium carbide daily. Workers were hired with desperate speed. Goodrich employed 8,400 people in January 1942. By June 1942, employment reached 14,200. By December 1942, the workforce numbered 18,700. The new workers had no experience with PVC. Most had never worked in chemical manufacturing. Goodrich established a training program. 1 week of classroom instruction, 2 weeks of supervised production, then full-time shifts. Helen Kowalski, age 23, had worked as a department store clerk before the war. She was hired in March 1942 to operate a plasticizer mixing tank. They showed me the valves, the temperature gauges, the safety procedures, she recalled in a 1989 interview. Then they said, "This material is going into life rafts that will keep sailors alive. Don't make mistakes." The working conditions were brutal. PVC processing required temperatures between 160 and 180 degrees Celsius. The factory floor routinely reached 40 degrees Celsius in summer. Shifts ran 12 hours, 6 days weekly. Plasticizer vapors caused headaches and nausea. Material shortages were constant. Copper for electrical systems was diverted to munitions. Steel for mixing tanks was reserved for shipbuilding. Semon improvised. Wooden tanks lined with PVC replaced steel tanks. Aluminium electrical conduits replaced copper. Glass-lined equipment substituted for stainless steel. Production numbers told the story. January 1942, 180 tons. March, 440 tons. June, 520 tons. September, 1,100 tons. December, 1,980 tons. Semon had promised 2,000 tons monthly by year-end. Goodrich delivered 1,980 tons in December, close enough that the War Production Board waived penalties. But promises were one thing, military qualification was another. The Army Air Forces established Technical Order 00-25-194. All materials used in aircraft construction must pass the tropical deterioration test. Specimens were exposed to 70 degrees Celsius and 95% humidity for 1,000 hours, whilst subjected to simultaneous fungal growth, salt spray, and ultraviolet radiation. Natural rubber failed at 780 hours, developing surface cracks and losing 30% tensile strength. Neoprene synthetic rubber, developed by DuPont, failed at 840 hours. Thiokol synthetic rubber failed at 650 hours. Semon's PVC formulation endured the full 1,000 hours with 4% strength loss. The results weren't close. The Army Air Forces issued contract W535-AC-25871 on 20th of March 1943. Goodrich would supply 12 million feet of PVC-insulated electrical wire monthly for aircraft production. Contract value, $6.8 million. Delivery schedule, beginning May 1943. Price, 57 cents per foot. The Navy had different requirements. Destroyers, cruisers, battleships, and aircraft carriers all used rubber gaskets to seal hull penetrations where electrical cables and piping passed through watertight bulkheads. Natural rubber gaskets degraded in seawater, especially in tropical conditions. The Bureau of Ships specification required gaskets to maintain watertight integrity after immersion in seawater at 35 degrees Celsius for 5,000 hours. Natural rubber gaskets lasted 3,200 hours before leaking. Semon developed a PVC compound with enhanced chlorine resistance. His formulation exceeded 5,000 hours with zero leakage. Contract NOBS 2847 followed on August 8, 1943. Goodrich would supply 840,000 PVC hull gaskets for destroyer construction. The Navy needed gaskets in 47 different sizes, each requiring custom extrusion dies. Goodrich built 47 die sets in 6 weeks. First deliveries began in September 1943. By December 1943, every destroyer launched from American shipyards used PVC hull gaskets. Combat validation came quickly. On February 18, 1944, USS England, a destroyer escort operating in the Pacific, was conducting anti-submarine patrol when a Japanese torpedo struck the stern, exploding 15 feet from the propeller shaft. The explosion ruptured the shaft housing, flooding the after-engine room through the propeller shaft seal. Damage control teams isolated the compartment within 90 seconds. The PVC shaft seal, despite complete structural failure of the surrounding metal housing, maintained sufficient integrity to slow flooding until pumps could compensate. The ship remained operational. Commander Walton B. Pendleton reported, "The PVC seal's flexibility under catastrophic damage prevented total flooding. Had the seal been rigid rubber, it would have shattered on impact. We would have lost the ship." The statistics validated PVC's superiority. The Navy tracked gasket failures across 400 destroyers built between 1941 and 1945. Ships equipped with natural rubber gaskets experienced 34 gasket failures per 100 ships annually, requiring dry dock repairs. Ships equipped with PVC gaskets experienced 2.7 failures per 100 ships annually. Operational readiness increased from 83% to 94%. Zero combat losses were attributed to PVC component failure. The Luftwaffe captured an American B-17 bomber intact in November 1943 after the crew made an emergency landing in occupied France. German engineers dismantled the aircraft completely, cataloguing every component. Technical Intelligence Report TIR 447, translated after the war, included this assessment. American electrical insulation utilizes polyvinyl chloride compounds of remarkable quality. The material demonstrates superior resistance to vibration, temperature cycling, and fuel exposure compared to German rubber insulation. Analysis indicates manufacturing processes requiring precise temperature control and plasticizer formulation beyond current German capability. Recommend immediate research program to develop equivalent materials. The recommendation went nowhere. Germany's chemical industry was collapsing under strategic bombing and raw material shortages. IG Farben's Leverkusen plant, which might have developed PVC formulations, had been bombed on August 1, 1943, destroying 40% of production capacity. The Ludwigshafen plant, bombed on 30 December 1943, lost 60% of capacity. Plasticizer production, which required petrochemical feedstocks, was impossible when Germany's oil refineries were being systematically destroyed. Worker expertise had been conscripted into combat units or killed in bombing raids. The window for technological catch-up had closed. The irony was profound. Between 1942 and 1945, the U.S. 8th Air Force flew 10,631 bombing missions against German industrial targets, losing 4,754 aircraft and 43,742 aircrew killed or captured. The strategic bombing campaign aimed to destroy Germany's production capacity for synthetic materials, including synthetic rubber. The campaign succeeded partially. German Buna S production declined from 15,000 tons monthly in 1943 to 8,000 tons monthly in 1945. But stockpiles, imports from still neutral suppliers, and desperate substitutions prevented complete collapse. Whilst American bombers died attempting to destroy German synthetic materials production, American factories were producing superior alternatives in unlimited quantities. Goodrich manufactured 47,800 tons of PVC compounds in 1943, 89,200 tons in 1944, and 118,000 tons in 1945. The material replaced rubber in 1,247 different military applications. Total cost to American taxpayers, $67 million in contracts. Total value to the war effort, incalculable. PVC electrical insulation, fuel tank liners, protective clothing, and hull gaskets were present in every American aircraft, ship, and vehicle operating in every theater of war. Waldo Semon never received direct financial reward for his invention. The patents belonged to Goodrich. His salary reached $8,400 annually by 1945, comfortable but not wealthy. He remained with Goodrich until retirement in 1963, eventually becoming director of research. The company honored him with internal awards and recognition, but the fortune generated by PVC flowed to shareholders, not the inventor. He died on 26 May 1999 at age 100, having witnessed PVC's transformation into the world's third most produced plastic. Global PVC production in 1999 reached 25 million tons annually. The material Goodrich management dismissed as commercially worthless in 1928 generated $20 billion in annual revenue by century's end. Every modern building contains PVC pipes, electrical insulation, window frames, and flooring. Every automobile uses PVC in dozens of components. Every hospital depends on PVC blood bags, tubing, and surgical equipment. Goodrich itself was absorbed by corporate mergers. The PVC division sold to multiple successors. The Geon Corporation, formed from Goodrich's PVC business, operated independently until 2000, when it merged with PolyOne Corporation. PolyOne continues producing PVC compounds at facilities in Ohio, Texas, and Kentucky, employing 4,200 workers and manufacturing 380,000 tons annually. The company's technical library contains Semon's original laboratory notebooks from 1926, yellowed pages documenting the experiments that changed industrial chemistry. The historical reversal was complete. Germany had pioneered synthetic materials research. IG Farben chemists had created Buna S synthetic rubber, nylon precursors, and polyurethane decades before American researchers. German chemical engineering was the world's most advanced in 1939. But by 1945, American industry had surpassed German capability entirely. PVC production in America dwarfed anything Germany could manufacture. The expertise, the factories, the workforce, the supply chains, all had shifted westward. An immigrant's forgotten invention, dismissed by his own company, had helped win a global war. Semon himself remained modest about his role. In a 1993 interview, he was asked whether he considered himself a war hero. "I was a chemist who solved a problem," he replied. The heroes were the workers who manufactured the material under terrible conditions, and the sailors and pilots whose lives depended on it working properly. I just happened to figure out how to make the molecules behave. The molecules had behaved well enough to help defeat the most technically advanced military machine in history. German engineering came in second place,